So let's start from our previous material. So we talked about the integral, especially the integration of two variable function. And let me lay out the definition again and then call it that double integral. The definition. So let f be a two variable function with real value. Be a function defined on a rectangular domain AB cross CD. So I gave you the most general form of definition of Riemann sum, Riemann integral, but let me rephrase that again. So if the maximum interval, maximum length of subinterval of x0 to xn, you know what that is. This is a subdivision of the x interval a to b, and that goes to 0. And if the subdivision of c to d, which is on the y-axis, and the maximum length of each subdivision goes to 0, and I'm taking the sum from 0 to n and 0 to m of xi star, yj star, of f of xi star, yj star times delta xi times delta yj, where now I have to explain everything before this is something, because I didn't say anything about xi's and xi stars, for example, and delta xi, of course. So here this xi is the subinterval from a to b, which is an increasing sequence, and also yj's are subinterval of c to d, which is also increasing sequence. And I'm taking xi, delta xi, for example, as xi plus 1 minus xi, which is the length of ith subinterval. Okay? And then delta yj as yj plus 1 minus yj. And I'm choosing a random point or arbitrary point, xi star and yj star, as long as it stays inside of xi plus 1, and yj star in yj plus 1. So this is our condition. So now everything is clear. Once you have the function f, then how to compute with a certain rule of choice of xi stars and yj stars. So if this exists, for any choice of subdivisions, and not only we have a freedom to choose the subdivision, which means that I can choose any subinterval or sequence from a to b, no matter what the length of subintervals are. I have freedom to choose these subdivisions. And also I have freedom to choose the points xi star and yj star as long as they stays inside of each of subdivisions, right? There are infinitely many ways to choose this xi stars and yj stars. And the assumption is that if I have a same value, not just exists and same for any choice of subdivisions and the xi stars and yj star, then we say the function f of xy is integrable on this two-dimensional domain, AB, which is also a rectangular domain. You have to remember that this is defined on the rectangular domain. And the limit, that limit, and the limit, let me call the name. So this is, well, let's say this is a star or asterisk, limit star is called the double integral of f of xy over AB CD. So usually when you write a mathematical statement with English, there are a few grammar that you have to use, but you have to be careful about on or over whenever you have something to describe. So I used over this interval when I used the word double integral, and I used the word on when I describe the function. So that's our definition. But first of all, if you have a definition, it's possible to check whether this limit exists for certain choice of subdivisions and xi stars and yj stars, but it is almost impossible to prove that given any function satisfies this condition of infinitely many choice of subdivisions and xi stars and yj star. So we have some theorem to actually guarantee that if you are given with some very concrete examples, for example, fxy is x times y, then we have to know, we want to know whether this function is integrable or not, just to start the computation right away before we worry about whether we can integrate or not. So here's the theorem. So if the limit when n goes to infinity of I from 0 to n, from j to n of f of, well, let's say I'm going to take our point xi star, not xi star. I'm going to choose just xi and yj. So I'm taking a left end of the subintervals instead of random point in between the subintervals. And then I take xi, not just delta xi. I'm going to make evenly divided subintervals. So I'm going to take b minus a. That's the length of nth, 1/n of the length of x interval, and b minus c over n. And that's delta n, that's delta y. So you see what I'm doing here. So here, where xi is nothing but a plus I times b minus a, and y, now it's j, so j is c plus j times d minus c. If I choose this specific xi and yj for xi star and yj star, and I take the value of x at this point and take the length of xi to xi star, which is all equal to these numbers, then exists, then I think I need one more condition. And before, and the function fxy is continuous on the domain AB cross CD. So continuous is required so that I don't want anything weird happen in between in each of these subintervals here. So suppose that I have a diverging point at some irrational point, and I choose my interval from 0 to 1 to n 0 to 1. And I chose this subinterval to be subdivided into integer number of amounts. And if I choose my xi star and yj star as on left end of each subinterval, I have no way I can find out that the diverging point is happening because it's on the irrational points. So I'm not getting there. So I don't want that happens. I don't want that any weird thing happens, and when I increase the number of subdivisions, then I don't want to miss those things. Weird thing happens. So I'm just eliminating all possible weird thing happens here. So continuous means that there's no divergence or there's no like oscillating and so on. Then it's a theorem. I'm not going to prove this. So it's a theorem from the analysis that you can, you have to know lots of mathematical concepts and assumptions and so on. Then the function is integrable. So it's a nice theorem. Now you have a concrete thing to check, right? So which means that you can only check that the limit exists for a certain sum. And this sum is nothing but of a function of n. So a, b, c, d are constant, right? So according to the a, b, c, d, we have xi and yj. Of course, they are a variable n. But that's what we are going to expect, that this is this whole thing, the summation goes to the function on n, right? And now we want to let n goes to infinity and see how limit goes. So we have concrete things to compute. So we can only check whenever the function is continuous, which means that there's no diverging point in the interval of domain, then this is the thing that we have to check whether to find out that this function is integrable. And moreover, and if this happens, then the limit, this limit is the double integral. So here, A, B, C, D. Instead of using the symbol D, I just put the domain itself and on the bottom of double integral sign, and then f x, y, dx, dy. So by the way, we also introduced the notation of double integral, which is denoted by, we have A, B, C, D, x, y, dx, dy. So after the last time, I was thinking about what I said, and then I was very disturbed, actually that's the right word to say, disturbed by what I said afterward, because this is the double integral, and I introduced one more notation, which is actually the notation for iterated integral, which are different concept from the double integral. And I kind of said that these are the same, these are kind of symbols that represent the double integral. And then I feel it's wrong. I mean, it's technically wrong, but I was disturbed that I said that. So I'm going to rewrite the definition. I already rewrite the definition. I don't want to put another symbol to represent the double integral. This is the symbol. This is the omni symbol that represents the double integral. Okay. And then also we had a great question. So one of the questions was that is there other ways to integrate? So this is a integration developed by Riemann, and I explained that there are other ways like Lebesgue integration and so on. But along with that question, I want to impose another example that. So we're going to talk about the function that is integrable from now on. But before we move on to the actual integrable function, let's talk about what kind of function is not integrable. So I'm going to define a function defined on 0, 1, 0, 1. And I'm going to put the value of xy as either 0 or 1. So 0 if x and y are irrational. Or let's say x and y. Maybe if I make it more okay, well let's leave it here. So and 1 if one of at least if x. So what's the opposite of x and y are both irrational? What's the opposite case? Opposite of irrational is rational, right? Rational. So what are rationals? Does x and y both rational? Or, right. So if x or y.
Yeah, so yeah, that.
Well, is it my computer? Is rational. Okay. So it's a function, right? So it's not a continuous function, but when you describe the integrability of the function, we don't impose a continuity on a function. So when you describe a differentiability of a function, then in order to have a differentiable function, your function must be continuous because it follows directly from the mathematical logic. But you can have an integral function when the function is not continuous. So this is totally discontinuous function. You don't find anywhere that is continuous. Because if you approach to a rational number, you always have an irrational number very close to that rational number. So there's always 1. Even though you want to go to 0, there's always 1 at the near point. So how would you compute the so you cannot apply this theorem because you don't have this condition. So you have to go back to the definition of integrability here. So think about this question. So well, you can take the division fairly easy subdivision, which is equally subdivisions. But the thing is that you have to put you have to choose xi star and yj star randomly so that these all limit should go to the same value. That's how you get the integrability of a function. Suppose that you have that. So you have f of I star and yj star. So in each interval, whether or not the left and right ends are rational or irrational, whenever you have a non-zero length interval, there are always the rational number and irrational numbers, right? You can always find two irrationals, one rational and one irrational, right? So depending on the choice of xi star and yj star, you can always make this function to be equal to 1 or 0, right? by suitably choosing this xi star and yj star as irrational or rational. So it's totally up to you to choose whether your value of function in the summation becomes 1 or 0. So if you choose your value of function always 1 by taking your xi star and yj star follows this criterion, then what's the summation? So you're integrating 1 over 0, 1, 0, 1 interval, which is a 1, 1 square. You have a height 1. So what's the integral? What's the limit? 1, right? So you're taking a volume of length 1 cube, right? So in this case, you get limit of blah, blah, whatever that is, that all condition. Doesn't matter now because, so this matters because the function changes, the value changes over each subintervals. We have all same values for every interval. So taking the limit doesn't matter now because we have all 1 value. So summation is just a constant. You're taking 1, constant 1 in this place, and you take out. And what you're doing is you're summing all this delta yj over j from 0 to m. That gives you the length from c to d, which is 1. And also you're summing all delta xi from I from 0 to, I'm sorry, so it's not n, it's not minus 1. You're summing all lengths of subinterval from a to b, which is 1 in this case. So you get 1. So there's no n survive. So no matter how you can take the limit, it's always 1. How about this case? You can choose your function to be 0. If you choose your xi star, yj star to be all rational, irrational in each subintervals. Okay? So you have, say I enlarged my subsquares, subdivisions of each this square box. And this is xi and xi star, and this is yj and yj star. No matter what these values are, you can always find the point where coordinates are both rational, right? Right? So we can choose xi star, yj star are rational. Then the limit is 0. You cannot make them equal. Actually, you can make your limit to be any number between 0 and 1. Because you can choose some portion of your subinterval, you can choose your function value to be 1, and some portion of subinterval can be 0, and so on. Then you can make any number, any value to be the limit. So at least this fact shows that this function is not integrable. Now, why did I bring up this examples? Because I wanted to show, first, I wanted to show that the example of non-integrable function exists. And also, second, there are other ways of defining the integration. So far, we always learn the Newman's integration. And people have been thinking about whether this is perfect, because intuitively, does it make sense? Well, definition makes sense, but if you think about the rational and irrational number in the one-dimensional space, one-dimensional line, you have a rational number and irrational number. So there are infinitely many rational number. There are infinitely many irrational number. Which are bigger? Which set of numbers are bigger? So the comparison of size of numbers of irrational number and rational number boils down to the comparison of size of natural number, 0, 1, 2, 3, 4, 5, and the size of real numbers. The real numbers are, it's like so many so that you cannot even like order them, right? You cannot make a label on it. So people have been developed the set theory about the size of a space, a size of a set. And they say that the natural number, the set of natural number is countable, which means you can actually count from 0, 1, 2, 3, 4. Like literally, you can count it 0. Number 0 is 0, number 1 is 1, and so on. But the set of real number is uncountable. You cannot make a label from 0, 1, 2, 3, and you're always missing some numbers by doing that. So uncountable set is far more bigger than countable set. And the real number consists of uncountably many irrational numbers. So if you randomly throw a dot, throw a, what do you call this game? That has a pin and then you throw it onto the board. Dot, is it the dot game? What is it called? The name? Is this called a dot? Anyway, when you throw something onto the real number line, then like not even 99% 9. You have 100% that your point is lying on the irrational number. There's no chance, almost zero chance that you have a particular P over Q rational number. Your point lies on the P over Q rational number. No chance, because countably many is far less than uncountably many sets. So think about this situation again. So even though we impose that X or Y is rational, you have far more set of elements that lies in this category. So if you measure, now it's a time when the thing about measuring thing comes up in the mathematics. The measure theory is it's called. So when you measure the set with set consisting of bigger set, and you count the size of each sets. I mean, the number of elements are all infinite, but if you really compare the size, like uncountable and countable and so on, and then all points on X101 lies on this category. This consists entirely all sets. Like a probability, if you just throw a dot on a 0101 square, you have almost 100% to lying on the point whose coordinates are irrational. So with this idea, if you try to at least draw, like you cannot draw it, but at least you're imagining a function, then you're looking at zero function. It would look like a zero function. There's some point that pops up at the rational point, but that's almost invisible compared to everything is zero, because almost everything is a point whose coordinates are irrational. So in the Lebesgue measure, if it depends on the integration depends on the measurement, the measure of the domain space, and the measure of this set, this subset on 0101 square is 1, meaning that the area of a set consists of this criterion is entirely 1, which is the same as the entire domain. Then in the Lebesgue measure, in the Lebesgue integration, this function is integrable, and the integration is 0. So I'm saying that there are other ways of defining integration, even for which is not integrable on the Riemann integration. Okay, so it's a side note, and then that was our material from the last time. Do you have any questions? So we are talking about the Riemann integral in the calculus. But I'm saying that there are another way of integration in analysis in a bigger area of mathematical fields.
You mean the method to choose one value for integration?
Yes, just you pick a random point or arbitrary point on each subdivisions, and then you try to find out that the limit always exists and same. Yes. So we'll get into that. I mean, we will talk about the non-standard example. The standard examples are one that can be integrable, and it's similar to what you have trained in a high school, how to compute the integration of this polynomial function and sine function and cosine functions. We're not going to talk about that. We're going to talk about what does not fall into the category that you have been trained. The part of our reason is that whenever you are going to do a research, and if the research is related to mathematical computation, you're not going to do it in your hand. Unless the question is so easy and you just want to see it fast, you have to use the computer or a computer program like a MATLAB or other coding program to find out the numerical computational result about the integration. And then way you do, if you are using sophisticated program, a calculating program, then you simply plug in the values that they have already developed as a function, and then you have to plug in the arguments correctly, and then they give you the answer. And then it's just a problem of how you plugged in the numbers or formulas correctly or not, right? But what you have to really understand is what's going on inside of that formula or function. I mean, you don't have to dig into the code, every single line of the code, but at least you have to know what's the idea of this function implemented in the programming or numerical computational tools. Because I'm worrying up the situation like this. So you have a project, and you want to model something relevant to your project, and you modeled by a formula, and now somehow you have to carry out the computation, like integration of that formula. You did something by plugging correctly to the computational tool, and you get some results. And you take the experiment, whether that simulation is true or not, and then the experimental result is nothing similar to what you have simulated by integrating the function through this numerical tool. And you have to find out why. And this difference between the huge difference or incorrectness of these two results might comes from not understanding when you can or you can't integrate the function over the domain. Like, this is the two extreme case, but I'm going to show you some cases when function is not continuous on some intervals, and if you try to integrate, at first glance it seems integrable, but actually you don't. You can't integrate that function. So you have to understand some exceptional case if you really want to pursue or do not want to make a mistake on your career. So let me give another definition, another definition. And then also I want to introduce some concepts of the integration. So let's say we have same situation. So we have f of xy, which is the real valued function, be a function defined on a to b C to D. Then I'm going to introduce the iterated integral. Of f over a, b, c, d is the following. So it's a number, but you take the integration of something like single variable twice. So for example, you take x and y, and so I should switch these the wordings here. So let me say it's either so you can take C to D first instead of A to D, A to B. So fxy. So let me erase this for now. So and then dx dy or A to B, CD, fxy, dy, dx. So when you say the iterated integral, it means this or this. Or if you say this or this, then it's called iterated integral. What does this mean? It's just a method, technical way of taking integration. So first of all, let's take this first. On this left-hand side symbol, we have inside of dy integration, we have dx integration. So in here, we have y variable, but I'm taking y as if it's a constant, as if it's the same thing as if when we take the partial derivative. So it's like you can take it as a partial integration, but we don't use that word. Okay? So it's integration over x as if y is a constant. Okay? So when you do, what do you get after you do the integration over x? You don't get any x anymore, right? But y is intact. I didn't do anything on y, so I consider this a constant, but it's not really a constant. So at the outmost level of integration, we have still y, like a function of y. So we're taking a function of integration over y. This is a single variable function, integration of single variable function. So we are taking integration of two integration over of the single variable function. The first one is as if I'm taking another variable as a constant, and then the next one is that it is actually the single variable function, right? And same thing for here. We have switched the order of integration, but the idea is the same. We have integration over x as if, y as if x is constant. Okay, so that's an iterated integral. So why do you think we have iterated integral? So in order to say that, I have to start with the question. We had an equation of a theorem of taking an integration, but that's complicated. Whenever you can't, if you want to carry out the integration by your hand, you can't always expect you have to do the limit and summation over large numbers and then compute these limits to find out the integration. You need a very the easy way to compute the double integral. So the reason why we introduced the iterated integral is this iterated integral makes the double integral, computation of double integral easier. So by theorem of Fubini, that let's say I have the same situation, but I'm going to rewrite this. Let z equals f of xy be a I don't think I need a continuousness of this theorem, but I'm just going to impose this just to be safe. Okay, so let f be a continuous function on AB cross CD. Then what? So look at the theorem here. So actually, I should put another theorem that if a function is continuous on A to B to C to D, then it's always integrable. I made some redundant assumption in the theorem, but anyway, so let me write it here. So it's not a part of Fubini theorem, but just make it into the same argument. Then this function f is integrable over AB cross CD, and not only it's integrable, it means that it has a limit of that summation, but you don't have to compute that limit because this double integral, that's what the integrability means, is actually same as computing this iterated integral, both of them, because both are equal. So AB, CD, f dy dx, or CD, AB, f dx dy. So there are lots of implications. So first of all, that if you have a continuous function on the closed intervals, closed domain, then it's integrable, which means that this left-hand side exists. And not only that, but this left-hand side can be computed from iterated integral in any order. It's all from the continuity condition of a function. But you have to remember that this is not just because of continuity. It actually lies on the fact that if function is continuous on a closed set, which means that it has a boundary, then it always has a local maximum and minimum, and not local, it has a global maximum and global minimum, which some of students already wrote in the midterm answers, that probably you searched Google about finding maximum and minimum, and probably you have seen this theorem that if a function is defined on a closed or a set with a boundary, and if it's continuous, then it always has a global maximum and global minimum. That means the function is bounded. The value of function doesn't goes infinite in this interval. So that's the essence of this Fubini theorem, but I'm not going to prove it, but I'm going to show you the idea why this is true. So anything not clear, please let me know. So maybe we can look up some examples. So for example, you are asked to explain what is Fubini theorem, or more principally, asked to explain what is the iterated integral. Then you can explain the definition in your own language, not just copying what I just wrote in the blackboard in the lecture, but the best way is you can provide example. Like, this is the way you can describe, but when you describe something, when you define something, especially in mathematics, you have to be able to reproduce an example or able to calculate some concrete examples. So for example, let's say I have a function fxy Give me any formula for xy, Jimin. Not too complicated. Which one? X plus y. Okay, that's fair enough. So we have x plus y, and let me give give me some interval or closed intervals. Juno.
From
0 to 2 for x. 0 to 2, okay. For y, right? So you have to check whether this formula is continuous on these domains. But it's true when x plus y is continuous on all the real numbers, right? So a real plane. So let's try to compute the iterated integral. Let's start with integration over x, right? What is this? So you take y as if it's a constant, and you're taking x as an integrating variable. So you get 1 over 2 x squared and yx, right? And then you take x from 0 to 2 and put it dy. And then 0, 2, and you compute this. You plug in 2, you get 2 plus 2y, and 0 is 0. 2 plus 2y dy. And now what? It's easy, right? What's integration over 2? 2y, yes. Y squared, 0, 2. So it's 8. So you can check the reversed iterated integral, and that makes the same thing. But let's try to, I erased it. So let's try to use the limit definition of double integral, right? The left-hand side is not defined as an iterated integral. These are two different concepts, okay? So in order to find out the left one, you actually have to find the limit. So 0 to, I'm going to use a theorem because the function is continuous. So I'm going to use the limit n goes to infinity. I'm taking n as a number of subdivision for x and y. And summation of I from 0 to n minus 1, j from n minus 1. And I thank for Jamin that he gave you this simple equation so that I can actually compute the summation after all. So I have to put f of xi, yj, but let's write it here. So xi is the ith number at the n subdivision. So we have n subdivision. Each of length is 2 over n, and you have ith component, an ith number. And then you always also have j's place for y-axis. And then you divide it into n pieces. So we have delta x is 2 over n, delta y is 2 over n, right? And now let's compute. So limit, summation, summation, and this becomes n over 2 ij, but there are 2 more n over 2, so I'm going to take 2 over n cubed. Okay. And taking summation is not hard. You just take summation from 0 to n minus 1 for both. So let's take a summation over j first. For I plus j, right? So n goes to infinity, and we have 8 over n cubed. And what's this? So you're taking summation of I plus j, I is constant, so you have n i's, right? And then you take the j from 0 to n minus 1, right? So you get in plus, how do you get the summation from 0 to n minus 1? N minus 1 n divided by 2. Right? Okay, so we have another summation. Write it here. So we have, if I take n outside because it's a constant, I only have summation of I from 0 to n minus 1. So I get the same thing here. So n minus 1 times n over 2. That's the summation of in. And how about, so parenthesis here. So how about summation of this part? This is constant, right? So you get n of these, right? N of what? N minus 1 times n over 2. And then you take a over n cubed after all. No, they are the same thing. So we get n squared n minus 1 times 8 n cubed. Now n goes to infinity. What's the limit? 1? 8. We have 8, right? That's 8. Same. Okay. So it doesn't tell you that the theorem is true because we only had one example. But I just said that you only get n, the function of n, after you compute all the summation, right? This is our formula for the summation, right? This all complicated summation becomes the function of n, the formula of n, right? So you just take the limit of n, right? You can do that. It's a concrete thing. You can compute the limit. And we also showed that for this example, the equality holds between double integral and iterated integral. But let's talk about, in a more general sense, in geometrically, why this is true. So let's say this is our graph of function, and this is our axis. And usually I put, so this is how I graph the function. And now we have the domain that we are integrating on. So we have A to B, and we have C to D, right? So this is our rectangular domain, and this is a graph of function. And when you take the double integral, we are taking an area, a volume, between the graph of function and the domain on xy plane. We're taking a volume. By taking the way you take the volume is in the double integral is that you chop up this rectangular domain into smaller rectangular regions, and then you take the small, thin rectangular cube over that small rectangular domain, and then sum those small volumes, and then hoping that if you increase the size of subintervals, then this sum of volumes of rectangles approximates the volume under this graph, which is just round surface, right? That's the idea of finding the double integral. Then there are other ways of doing that, finding the volume. First, you take the slice parallel to x-axis, like this slice. Okay? And so this slice located at y, okay? And you're integrating x from a to b and trying to get this area. How do you get this area?
By taking integration with fixing y variable.
Right, by integrating over x. This is because you had an area by integrating a single variable function. Right? Area under the curve is the integrating of a single variable function. So this is integral of f. Well, let's say y is somehow misleading, so maybe I can put y0 for now. But I'm going to change it to y after all. But let's say I fixed y0, and then I'm going to find out the graph of a function by choosing choosing y0. Then x is the only factor that changed the value of function, so it becomes a single variable function. So if I take the integration over this single variable function over a to b, then I get this area. Now, I can think about the volume as the stacks of these slices. So at each point of y, I have area right here. So if I want to find the volume, then it's, if I take a small increment on y, like delta y, then I can make a small volume. Of course, it's not going to fit into exactly the volume underneath the graph of function, two-variable function, because now it's like a piece of cheese bricks, right? But anyway, if I let this delta y very small, then I can make the summation of the area. Let's say I gave a name for this. Let's say this is the area of a slice at y0. But now I can now erase y0 because y can be changed, so it's not constant. So I can add all these areas times the width of y, delta y. And then the summation depends on how many summation you had, how many slices you had. So this is the entire volume, and it is approximation. And then this is nothing but Riemann sum of single variable function. So this volume is actually becomes sum, so sigma becomes sum of ay and dy. And where y runs from here from C to D. Right? So we place the ay with this integration, then you get C to D, A to B of f of xy dx dy. That's how you get the iterated integral. And then it makes sense because all we are doing is finding the volume just by doing it different ways. If you want to change the order of dx dy, you can slice the other way around. So if first slice parallel to y and then try to integrate over x. Then you get a reversed order iterated integral. But obviously, that should give the same answer because it's all about the volume underneath the graph of function. Now, it should make sense whenever you're talking about the graph of function which is continuous, right? But what happens when you have a non-continuous function? So we saw the example that works, the Fubini theorem. We are going to see the example where the Fubini theorem doesn't work. So usually it's called a non-example. So I don't know where this word comes from, but usually mathematicians use non-example. It doesn't mean that it's not an example, but it's like example which doesn't fit into the explanation of theorem, or example that showing the failure of the theorem because of failure of the condition assumed in the theorem. So think about the function fxy. So this is very standard example that you can even find it in the Wikipedia. Defined on 0101. Okay. So there is a one point that this function is not continuous. Which point is non-continuous point? Origin, right? 0, 0. So whenever you have 0 on the denominator, everything makes it weird. So unless you have x and y are not 0, that's fine. Okay. So the thing is, you can define the Riemann sum. Okay. The only problem is that when you choose your xi star and yj star, is at some point becomes 0, 0, which means that at the beginning, if you choose your x0 star and y0 star as zeros, then this summation doesn't make sense. But you don't have to choose your x0 star and y0 star as 0 and 0. You can choose any number between 0 and n over 1 or something like that, 1 over n, something like that. So Riemann sum is defined. You can define your Riemann sum and then try to take the limit. We're going to see why that fails after all. So if I spoil you that this function is not integrable at all, but it's not satisfying the Fubini's theorem. So let's try to think about iterated integral. So we have x squared y squared square x squared y squared, and try to integrate over x first. What do you get? So basically, I'm taking an antiderivative. It's a function that has a derivative equals to x squared minus y. Right? Yeah. The derivative equals to x squared minus y squared over x squared plus y squared squared. What kind of function is that? So maybe I can start with the denominator of x squared plus y squared and some rational function. But then if you have a rational function, that the standard formula for taking derivative is that you take the square on the denominator and then do something on the numerator. So you get the denominator of x squared plus y squared squared, right? So the problem is what should go on to the numerator to get this. So consider again, I'm taking integration over x, considering y is a constant. So when you take a derivative here, you're taking a partial derivative on x. Okay? Consider y as a constant. How about x? Maybe I try with x. So if I had x, then if I take the partial derivative on x, what do I get on the numerator? So, what do you get? Taking partial derivative of this. Partial derivative. Right, but after all, you have to, if you simplify that, then what you get in the numerator part, assuming that the denominator is same as this, what do you get for the numerator? You have to actually carry out the computation. You can't probably do it on your head, but when I ask the question, I'm asking you to write, at least try to compute. Have you done it in your head, or? No, I'm trying to take the partial derivative because I'm trying to take there's no word partial integration. There's no word like 부분적 분리. It's just the integration over x, assuming the y is constant. So I'm guessing that this is our result. That means if I take the partial derivative of this by x, then I should get this. Do I get this? I'm asking this question. Do I get this? Yes? Uh-huh. Yes, minus x. Yes. If you try that without x, you will get y squared minus x squared. Just try to do that. Okay, so just watching it doesn't make you experience. You have to actually do the work. Okay. All right. So so what's this? When I have to replace x by 0 and 1. So minus 1 over 1 plus y squared, and I plug 0, it's 0, right? And then, therefore, this becomes 0, 1 minus 1 over 1 plus y squared dy. And what's this? Not sure this is a part of a high school curriculum. Have you learned this, Juno?
I haven't, but I think we already learned it at first semester, and observed that is tangent something.
Right, yeah, you remember correctly, yes. So it's the arctangent of y. So when I plug y equals to 1, the arctangent of 1 is pi over 4. Right? So it's minus pi over 4. And arctangent of 0 is 0. So it's a result, the answer is pi over 4. So that's when you take the integration over x first. Let's take the integration over y first. dy dx. Now, I have to take the integration over y. Okay, that means I have to get a function that gives this integrand when I take the partial derivative on y. Let's try x squared. That should be similar to that one. Let's try y over x squared plus y squared. Does it make sense? So when I take the integration, so you don't have to worry about the denominator. Let's talk about the numerator part. So when I take the derivative of y, it's 1. So 1 times x squared plus y squared, and minus of y times the derivative of y squared, which is 2y. So I have x squared survive, but there is also y squared, but it's subtracted by 2 times the y squared. So I get the numerator here. So this is the integral, partial integral. I said this, but okay. So there's no word like partial derivative, partial integral. Okay. Okay. So you have 1 over 1 plus x squared dx, and this is equals to. Now we have only differ by minus sign. So we have arctangent of x from 0 to 1. So that should be pi over 4. So when you take the integration over x first, you get minus pi over 4. When you get the integration over y first, then you get pi over 4. They are different. The Fubini theorem doesn't work. So that means you cannot find any reasonable volume by taking this iterated integral or by taking any Riemann integral or double integral. Why it fails? What's the problem? Because this function is not continuous. Why not continuous? Non-continuity matters. Why does it make it fails? Because if you have, well, first of all, if you should try to graph this function, but you can imagine how this should look like. Of course, in x and y are equals 0, then it should diverge. But think about the situation when x and y are same, or at least the absolute values are the same. So we have y equals to x line here. So this is x-axis, and this is y-axis. And then this is z-axis. This function has 0 when x and y are equal, right? Whenever x and y are apart from the origin, then the value is 0. And the value is positive when x is bigger than y, so it's going to be positive on this side and negative on this side, right? And then if you approach the origin from y goes to x line, probably maybe it goes to 0. Maybe. That's how a limit says. But if you are away, stay away from this line, you have nothing but going to diverge. You have nothing but the value diverges because this numerator part is way smaller than the denominator, because as this gets less than 1, and this also is small, but this is also getting to the 0 faster than this one. So you have something like, I cannot draw it, but I don't know how to draw this, but maybe if I try, something like this. So we had a graphing calculator, we made a program code for graphing some functions. So try graph this function if you have done this programming assignment. So that means if I approach to origin, it goes infinitely large. It keeps getting larger and larger. So what makes this problem? Why this makes problem? So let's try to draw x and y coordinates and x and y plane here, and try to enlarge around this origin. So we have quite a large picture here, and you have 0, and let's say we have 1 over n, and we have 1 over n, and it's quite large. And let's try to pick, assuming that I'm trying to pick a point on this first region of this entire 0, 1, 0, 1 region. And I cannot choose 0, 0 because that doesn't make a valid function value. But I can choose, like say, a point very close to 0, but not 0, inside of 1 over n, 1 over n. Let's say I'm choosing 1 over n square, like 1 over n square, right? That's a valid point, because if n is large, I mean, in any value of n, because it's an integer, it's always less than 1 over n, right? So let's say xi star and y0 star is equals to 1 over n square and 1 over n square. And of course, I'm assuming that the interval of subdomains are all equal to 1 over n for simplicity. And there are lots of summation, at least there are n squared summation, but I'm going to look at the first one when I equals to 0 and j equals to 0. Two indices are 0. That's when I have this subregion. Then f of x0 star, y0 star times delta x, delta y becomes what? So plug in here. Sorry, so I cannot choose the same way. This is 0. So let me choose it maybe 2, like this, okay? So if n is quite large, I mean, at least if n is bigger than 2, then this always lies inside of 0 and 1 over n. And I don't want x and y to be equal. I don't want to stay in this line. I want to stay apart from line. So that's my point. And then if I plug in there, we have 1 over n square square, and sorry, so x is 2 over n square. So 2 over n square square, and 1 over n square square divided by 2 over n square square plus 1 over n square square and square, right? And then this is 1 over n square. So we have what? 3 over n fourth, and here we have 5 over n fourth n square, and that's 1 over n square. We have lots of n's in the denominator, so it's basically 25, 3 over 25, and we have 8 on denominator, and we have 16 on the numerator. So we have basically 8 on the numerator, so n 8, right? Okay. So that's the first summand, right? The first summand in the summation, the huge summation. And that it already contains n eighths, n to the power of 8. And it's so big that it could be like 10 to the power of 10 power of tens or something like it. It's almost, it goes to infinity anyway, right? So no matter how you subdivide your region 0, 1, 0, 1 into smaller and smaller pieces, you can take a point in a first region that the first summand is so large that it can dominate everything else. Like, doesn't matter what other values are. Okay? So you cannot find a double integral for this function either, because it's partially because it's not continuous. But I want to make another point that not every non-continuous function is not integrable. Right? So which means that there are some non-continuous functions which are integrable. For example, let's say I have function x and y to be 0 or 1 when x and y is not 1, 1, and 1 otherwise. So except for 1, 1, 1, the function has value 1. So and this function is defined on 0, 2, 0, 2. So if you try to graph the function, then you have x and y, z, and here we have domain 0, 2, 0, 2, and the graph is a flat graph, flat surface, like flat plane, but at 1, 1, which is in the right at the center of this domain, there's a hole, right? That's the graph. Okay, so how would you integrate this? How would you take the double integral by taking the limit? First, you take the slice it. I mean, first you take the small pieces, small regions by chopping off x and y coordinates, right? And then you take the square, the volume of rectangular, thin rectangular cube, right? The problem is, if the rectangle lies on the region that does not contain this 1, 1, doesn't matter because it's always has a height 1. But if the rectangle lies on the subregion which contains this 1, 1, then you have a chance that you can choose your xi star and yj star equals 1 and 1 so that the height becomes 0 instead of 1, right? But that is negligible if you take the number of size of this number of subintervals goes to infinite, because this area underneath this rectangle is becoming smaller and smaller and then eventually becomes 0, right? So that's a negligible effect on this entire sum and the entire limit. So even though I put one non-continuous point, if you put the finitely many non-continuous point, it's all the same thing. So you can't neglect the effect neglect the consequence of choosing the point at the non-continuous point. So by this example, I'm saying that not always your function should be continuous in order to be integrable, but at least the function should not diverge at that point. Like if I had like thing is diverging at this point, like continuously diverging, then I cannot make the same argument anymore. But at least if you have one point is problem, then it doesn't make any change to the integrability. So yes. What? So one whole is not equal to 1, 1. Sorry. Yes. So I'm trying to say this other way around. It's okay. So, or it should be easier to put the equal mark here, but anyway, the same thing here. All right. So what I'm trying to show you is the way to compute the double integral. So today we introduced iterated integral over the rectangular region. So Fubini's theorem says that the double integral is equal to the iterated integral over the rectangular domain. But there are another version of Fubini's theorem that it says that the double integral on the rounded or non-rectangular region is also can be written as an iterated integral, and that's gonna covered in the next time. But for now, we're going to implement our method of double integral into Go code, which is going to be the assignment for the programming assignment for the class. So before we move on, if you have any question, I can answer. Yes.
So is there, this is my personal question as well. Is there any chance we can induce the fundamental theorem of calculus from the Fubini theorem? Because
From Fubini theorem.
I thought it was quite, I mean, the iterated integral is kind of it is more simple and it is rarely usable. But the intuition, the first fundamental intuition came from the Riemann sum. So I thought there was really correlated, just like the single variable function.
Right.
Fundamental function.
Right. So, very good question. Very good question because it brings a lot of questions. Another question. So, the question, if I repeat, is that if we can use, can we use Fubini theorem to generalize the fundamental theorem of calculus on the double integral? So, first of all, that question should be elaborated. Another question, which is, do we have a version of fundamental theorem of calculus on the double integral? Okay. So to answer that question, so first of all, the fundamental theorem of calculus is about finding the definite integral is defined by the difference of two antiderivative, value of antiderivative. When you have a concept, when you have like fundamental theorem of calculus, there are ways to generalize. So for example, if you have an integration over single variable, we generalize to integration over two variable, and that's a double integration. And if you generalize to three variable case, then it's a triple integral, and so on. So another way of generalizing the integration over single variable is the line integral. So basically, what you're doing in the integration over single variable is that you're moving your x point, which is an input of the function, along a line, which is a straight line on the x-axis, and then try to add up all the values of functions, right? So you can generalize the idea to two-dimensional or three-dimensional. So you're trying to put your point on the two-dimensional plane and try to follow your line along the curve, or trying to follow your point along the curve. So that's a one-dimensional thing. And then try to add up all the values of a function along this curve. So that's the concept of line integral. So if you generalize your single variable integration to the line integral, then you can say about the fundamental theorem of calculus, how to generalize to the line integral. And that's exactly, actually, you'd know this because you have a gravitational force, and that's a conservative force. I mean, that's the right word, maybe. Conservational vector field, right? That's how you put it, not conservative. Anyway, so you have a gravitational force, and moving horizontally doesn't change it doesn't change your energy state, right? Your energy state only matters on the height, right? So when you want to move object, I mean, if you have a gravitational force on this vertical force field, and then try to move your object from this A height to B height, then the path doesn't matter, right? You can just compare the height of these two objects and then try to find the energy, the potential energy, and then try to find the difference. And then that's that's the work you have done to the object to move your object from here to here, right? So how you calculate the work done is the contour integral, line integral in the physics. But in the physics, maybe they proved it or not, maybe, but they already said that this energy difference is I mean the work done is same as energy difference, the potential energy difference between this A point to the B point, right? So you can just subtract the energy at the B point and energy at the A point to compute the work done, right? That's the fundamental theorem of calculus generalized to the two-dimensional case. But if you have a three-dimensional thing, three-dimensional situation, you can do the same thing with the three-dimensional curve. I mean, the curves lying in the three-dimensional space. Yeah, so you can generalize it, but the Fubini theorem, at least, it's not about this line integral. So it's hard to fit your Fubini theorem or any iterated integral to the line integral case. Okay. It's a very good question. So all right. So do you have any other questions? Okay, so if not, then let's look some Go. So it's a long time since we have exercised some Go coding. So let me say, okay, so new file. I want to make a new project. Oh, this is okay. So it's a Visual Studio Code. Sorry, so I confused with the Golang, which I use often for Go programming. So let's say I want to make a folder for integration. Well, let me say integration. I want to make a new project here. Okay. All right. So I'm not going to define any sub-packages. So I'm going to work on this just main package here. Package main, function main, that's all. Probably I need one or two functions outside main. But what I'm trying to do is trying to compute the double integral of the function that we have shown as a non-example of Fubini theorem, which is the function x or y float 64. Oh, okay, so maybe I go slow on this and then try to let you to follow up on this programming. Because the best way to learn program is to repeat, like all. I'm giving you time by saying jargon here. So, like all exercise or like physical exercise or learning musical instrument, the best way of learning is not by watching someone else playing, but you have to do by yourself, but not just by randomly, but you have to follow what other people are doing and try to mimic, or at least try to do similar, what other people are doing. Okay, probably this is enough time for you to prepare this programming environment. All right, so and then it spits another float value. So I'm going to give a formula here. So the numerator is x squared plus y squared minus y squared, and then denominator was x squared plus y squared. And I have to take a square, but don't use this. This is only works for MATLAB. I'm going to, there's a math power function on a math package, which is also the standard library, but I don't want to use that. I don't want to use I want to use as few packages as possible. So this is how you can implement our function, right? And then what? So what I'm trying to see is, so when you actually implement the double integral by taking the limit, the computer cannot take n goes to infinite, right? The infinite is not a number, so you have to fix a number of n, number of subdivisions to compute the summation. So I'm going to increase the size of each x and y subdivisions and then see how this summation goes. So let's say I'm going to take 100 subdivisions for each dimensions, and thousands and 10,000s, probably 10,000 is the maximum that I can choose here, considering the computing power. So 2 to what? 10,000 means 10 to the 10,000 is fourths, right? So I'm going to go I from 2 to 4, so less than 5. So and then so let's say I take n equals to 1. So n is the number of iteration, but I have to take it as a 10 to the power of 2, 10 to the power of 3, 4, and so on. So I have to pick another iteration saying that I'm going to multiply 10 by that much number of I times, right? So now I get the number of number of subdivisions as n here, okay? And then I want to print something because I want to see the value. So fmt dot print f. So printf is standard printing strings command. So first of all, I want to specify the number of subdivisions, and then I want to specify the value of double integral, and I have to implement the function for the double integral of this function. So I'm going to give a double integral function. So this double integral function is taking the argument, which is the integrand function f, which already defined outside of this loop, and also the domain. I'm going to put a domain, 4 numbers of our domain here. Then also lastly, the provided with the number of subintervals. So you see there is a red marks here, so FMT, because it's not imported, because I didn't put the import packages here, import FMT here, okay. And then there's another red mark here. Well, this appeared right here. I didn't define this function, so it will be problematic if I don't do this. So I'm going to write a double integral here. And it takes an argument, 6 argument. The first one is the function that of this form. Okay, so it's a function that takes 2 float values and then spits us float values. So basically it means that it's a 2-variable function. And 4 float values, so you have to put 4 floats here. 1, 2, 3, 4. And the last one is n, it's an integer. Okay. And then it spits the float value as the value of double integral. Okay, so that's that. Then I have to give a name for each input. So I have A, B, C, D, okay, and N, okay. All right. So let's say I'm going to define my dx as b minus a divided by n. The reason why I have to put a float 64 outside of n is that n is the variable of type int, and I have to change it to float in order to have an arithmetic between float values with the float values, and d minus c divided by float 64. And then let's try to compute the value. So value is the place where we're going to store the value of the double integral. But what we really do is not sending the limit, but I'm trying to take the summation, okay, with a large n. So n is provided. So I from 0 to n, so that counts n indices for x-axis, and j from 0 to n, and that counts the indices for y-axis. Okay. All right. So and then for each and x and y, each I and j places of this subregion, I have to choose xi star and yj star. I'm going to call it as an x and y. Okay. So now you have to pick a random, arbitrarily choice, but you can choose it randomly. But let's try with a fixed way of choosing this xi star and yj star. I'm going to choose a midpoint in the region. Okay. So with a plus float I, so I is an integer in the for loop, but I have to change it to float type. So I choose this. And then dx, so that's the xi. So in the subdivision, xi, not xi star, but I'm going to choose xi star in the midpoint. So dx, I'm going to add it with dx over 2. And same for y. So y from float 64, j times dy plus dy over 2. Okay? And that's my xi star and yi star. I'm going to add that to value, the val here, with compute of x and y times dx times dy. Right? And then when they iterate every for loop, then the value which added with the f dx dy is our double integral, summation of double integral. So I'm going to return that value. Okay. So if I show you briefly about this argument, the double integral takes the function of this type, and I assign the name as f. I think it's the same name as I defined in the main package, but these two functions are different functions, and this f are local variables, so I can use the same symbol here. And a, b, c, d are defined as the limits of x and y interval, and I have another last one, the n, as a number of subintervals, and n is used here, and it spits the float value as an output. So that's stored in the val, and then I return the val. Okay. All right, so let's look at this one. Oh, so I forgot to line break. Okay, so we have y. Yes.
I'm trying to figure out why there is dx over 2 and dx dy over 2
At the end?
in 404J. That's the
Here. So I'm choosing a midpoint. Midpoint. The center of the region, subregions. Because if I choose the left end or left bottom corner of the region, then I end up getting 0, 0, which is not defined. I'm going to get not a number error, so I don't want that. So another way of choosing the value is either you choose a left top corner or right top corner or anywhere else in between inside of the region, but I just decided to choose a center as my xi star and yj star.
So you are trying to choose the middle point, the subinterval.
Right, right, the center of the region. Yeah, I don't know why this make a problem here. So usually yellow is just a warning, so I think there should be no problem. All right, so that's all. So have you followed so far here? Let's try to run this code. I think formatting is something wrong. Print F. Oh, I forgot N here. Okay, sorry. So this D, the %D is the format for the integer. So I'm trying to put number N at front, and then the value of double integral. So that's how we get these here. All right. So main again. Okay, you get all 0. Wow. So it seems like the double integral exists and the value is all 0. Okay. So is it really 0? So that's the problem when you try just learning techniques of integration and then not knowing what's going on inside mathematically, then you probably end up concluding that this double integral is 0, because that's what this program tells you, right? Now, let's try to put a random point in each region by using rand float 64. So rand is from math package, math rand. Okay. So I'm using a standard package rand inside of a rand math package, and float 64 gives you random value between 0 and 1, a random float value between 0 and 1. So because you're not getting actual 0 or 1 by taking a random function, so it will take a point inside, not on the boundary, inside of each subregions. Okay. Now let's take the run. It takes some time because the rand function is a costy function. So we have weird values. It's not consistent at all, right? It's changing. If you run it again, you get the same value. So only because the rand function has a constant seed. So if you have to change your seed of random generators to actually create a real random functions. Okay, so let's change the seed. So rand has seed function. So seed needs an integer seed, and usually how you seed the random generator is the current time. So I have the time, and now time now returns integer 64, but I have to change it to Unix nano here. So I'm going to import time, and that's how you seed time. Okay, so yeah, that's how you seed the random generator. And let's now run the code again. So you have a different value now. So now it works with real random values. And every time you run it, you're not getting a constant value. So it's just because this function is not continuous at 0 and 0, and weird thing going on at near 0 and 0. If you work with a continuous function, like continuous on the boundaries also, then you're not getting this type of situation. So for example, let's say I change all of this to simple x squared plus y squared. Okay? Then, if I run this, I get 0.66671 to 6667 and so on. So as I increase the number of n, it gets more accurate. You get more accurate decimals of the value of double integral. That's the normal situation because x squared plus y squared is continuous on x 0, 1, 0, 1 and also is continuous on the boundary point, right? But the previous situation is indicating that if you take the Riemann sum, you don't get a constant value of limits. So it's not integrate. You can guess that this is not an integrable function, and you can actually check mathematically too. Okay, so that's how you integrate double integral. I didn't say about the iterated integral. We can probably work on the iterated integral once we learn next time how to use the iterated integral to compute the integration over non-rectangular regions. Okay. All right, so this is, I think I should stop here. And by the way, so there's this really important announcement. The next Tuesday, we don't have a class because I have another. So these period, there's an application. There's what is it called? Interviewing season. So it's from Tuesday to Thursday. So we don't have a class on Tuesday. We're going to make up at some point. Anyway, so let's meet on next Friday and have a nice weekend and see you next week.